Welcome to Math 3000. I hope you guys are doing well. So today the plan is to continue talking about relations, in particular equivalence relations, and maybe get into talking a little bit about equivalence classes if we have time at the end. Any questions about things before we get started today? Let me see. There's something chatted. Never mind. Okay, so then let's kind of pick up with where we left things off. So we talked about the properties symmetric, reflexive, transitive last time, and then we did talk about if a relation satisfies all three of those properties, then we call it an equivalence relation, and we'll kind of see why those might be nice properties today. So if we have a given relation R, and we want to prove that it is a relation, equivalence relation, then we've got three different things that we need to prove. So we need to show that it's reflexive. So that would be like a for all statement. For any x in the set, we want to show that it's related to itself. We want to show that it is symmetric. And symmetric and transitive, these are implications, so they're if-then statements. So we can prove them directly, contrapositive, contradiction. But if we do them directly, then we can kind of assume that x is related to y, and then we want to show that y is related to x. And over here, the assumption is two things, and then we would want to show that conclusion over there. So I want to start today by practicing this proof technique, these proof techniques here of trying to prove that something is an equivalence relation. So we started last time kind of laying out the plan using the equal relation. I am going to just adjust it. So let's just kind of take a look at the first one. I think looking at the equality relation maybe might be so trivial that we might not actually see what is going on in the proof. So I want to prove this. Let's think about the parity relation. Okay, and so again, by this parity relation, we mean that two integers are going to be related if and only if they have the same parity. Okay, so we have things like this. So we want to prove that this relation, we talked about this last time, that it does satisfy all those properties. So if we want to prove this, then for the reflexive proof, right, then we want to show for any arbitrary element in the set, it's related to itself. So here we are working with things that are integers. We're going to take any arbitrary integer. Instead of saying equal here, what we want to show, I'm not going to write this out, right? But the goal here would be we want to show that A is related to itself. And I'm going to call this relation P here. That's what we would need to show in order to prove it is reflexive. And so if the relation here is the parity relation, how can we argue that A is related to A?
Just by proving it is either even or odd. Therefore, itself is even or odd.
So an integer is even or odd, right? Right now, I have one integer A. How do I know that A is going to be related to itself? What would need to be true in order for A to be related to itself?
just as simple as A equals A?
So 2 does not equal 4, but 2 is related to 4 through this parity relation, right? So we're not dealing with an equal here. So, here's the parity relationship. X and Y are related if they have the same parity. So what would I need to show in order to show that A is related to itself by this parity relation? Or conversely, what would it mean for A not to be related to itself by the parity relation?
Is it like A is always even or always odd?
So A is even or A is odd. Okay, that's right. So integers are going to be even or odd. The question is, why is A related to itself by the parity relation? What would need to be true if I say X is related to Y? What does that tell us about those two integers in general?
They're in the same set?
So they're integers, right? And if they're related by this parity relation, then what does that tell me about these two integers?
Would we need to do two cases where they can be rewritten as 2x and 2y, or 2x plus 1, 2y plus 1?
No, I'm just trying to get at what this relation is here, right? So we wrote out some examples. So according to how this is written here, X is related to Y if and only if they have the same parity. So that's why these are related and these aren't. So if I want to claim that X is related to Y, then by definition, what would I need to show? I would need to show that they have the same parity. 3 is related to 9 because they have the same parity. 3 is not related to 8 because they don't have the same parity. So if I want to claim that X, if I see this written over here, this tells me what is true about X and Y. They have the same parity. That's it and only, right? It doesn't tell me anything else in addition to that, but that's a lot of information. So if I see that X is related to Y by this parity, that means they have the same parity. So if I want to prove that A is related to itself through the parity relation, what should be true about A and A? They should have the same parity. That's right. Does A have the same parity as itself? It does, right? There's no number which is even and odd, or even and not odd, right? I mean, A is a number, it's one number, it's either even or odd, and it's going to have the same parity as itself. So we don't need to go too crazy here.
I think we're stuck in thinking that we're now assuming what we were trying to prove, and maybe that's why I was getting confused.
So the only thing that we're assuming here is that it is an integer. And that's it. But this doesn't mean that we need to like disavow all previous knowledge of numbers and start from scratch. We know some things about numbers, and we're allowed to use some of those things. And so, for example, totally fine to be clear with the fact that a number has the same parity as itself. It's fine to say A is equal to itself. Really hard to prove that because it's just so obviously true. So there are some things that are like axioms that we would treat as fact that we don't actually need to prove. So yeah, the fact that A has the same parity of itself, maybe you guys are getting twisted up because that's so obvious. I don't know. But I think the thing that I want to be sure of that we're getting at here that we need to know is like, what does it mean? This thing P can mean different things in different places, and the A's can be different things in different places. They might be different sets, they might be different relations, but we need to know how that relation is defined before we can think about proving various properties are going to hold or not hold. Okay. Any questions? Okay, so let's see. So then for symmetric, this is an implication. Okay, and so here we want to say, okay, if I assume that I start with two integers, a and b, that are related to each other by this parity relationship, then we would like to show that they're related in the other way. And in this case, we're thinking about the parity relation. So again, we can try and do this contrapositively, contradiction, other methods. I think direct proof here is going to work just fine. So we don't need to go through any logical pretzels to get there. We'll just try and do this directly. So when we're proving symmetric, the technique here would be, well, let's suppose that we have a and b are integers. We need to define what these things are. And we're going to suppose that a is related to b. And again, the goal here would be to prove that it follows when we flip the ordering around Okay, and again, let's like not make this any more difficult than it needs to be. So all we really want to do, I think, when you're working with these, it's like other proofs, is maybe let's just like start by writing out the definition of what it means to be here, right? So like usually these proofs, the next sentence follows from the previous one. So if I suppose this, then by definition, A being related to B tells me that A and B have the same parity. Just taking it word for word like what was given over here. So this means X and Y have the same parity. So over here, I've got A and B. And that's pretty much all we need in order to say that B is related to A, right? By the same relation. So basically, if you want to capture kind of the symmetry of this argument, really what's going on is since A has the same parity as B, and again, this is just kind of based off of what we know about even and odd numbers. So maybe as the relations get a little bit more complicated, these arguments might get a little bit more complicated. Right now, it's really just like one sentence connecting the assumption to the conclusion. Any questions? Okay, and I think you maybe could imagine like how could this go with contrapositive, right? You could suppose that B and A don't have the same parity, and that's going to imply that A doesn't have the same parity as B. It would be essentially the same proof. So it just looks a little bit cleaner to do it directly. Okay, so great. So then for the transitive property, right now, again, it's a implication again, but here we assume two relations, and we're going to try and show a third one. Okay, so here we can start by supposing now we've got three different things. And these things in this case are integers. And at this point, we haven't claimed anything about A, B, and C themselves other than they're integers and have this relation. So we saw last time that at this point, this doesn't mean that A is different from B is different than C. They could be the same element. They could all be equal to each other. So let's just keep it really arbitrary. A, B, and C are integers. They might be equal to each other. They might not be equal to each other. We're going to prove this no matter whether A, B, and C are the same or not. So all we know about them is that A is related to B and B is related to C. And again, the goal here would be to show that A is related to C. And I think, we could be really thorough, I suppose, and do this like with cases. Case one, A is even, right? Okay, well then if A is related to B, then B is even. And if B is related to C, then C is even. Therefore, A and C are both even. And then we could do case two. A is odd. Okay, well then B is odd. And you would see that if you broke those up into two different cases, the even case and the odd case, the proof is identical. You could just replace each even with an odd. So when we have things like that, I think that we can be safe just covering both of those two cases together and not have to worry about whether it's even or whether it's odd, because the logic works the same. So I'm just gonna do this in general. I'm not gonna assume that A is even or odd. All I know right now is so this tells us that A and B have the same parity. And that's really what we needed to get to in order to say that A and C are related by the parity relation, is we needed to get to the point where we have proven that A and C have the same parity. So on this proof kind of here, we're just using same parity instead of like a case where I put even everywhere versus a case where I put odd everywhere. And so once we've proven all three of these properties, then we've proven that this parity relation is an equivalence relation. Okay, any questions? So it's fun. You get three proofs for the price of one here. That doesn't happen much, so that's good. And yeah, I would say they get increasingly, though it varies depending on the relation, but yeah, I would say traditionally, if you are wanting to know what you're getting into in these proofs, I would say, reflexive is probably usually the easiest of them, and transitive has the most moving parts. That usually is a trickier one to prove. Okay, any other questions about this example?
Yeah, for we only do like all three for equivalence relations only, right?
We need to check all three of these to check whether a relation is an equivalence relation. Yeah.
Okay, cool.
So last time we were kind of just thinking a little bit informally about these relations, like what do they mean? What are some things that satisfy them and don't satisfy them? And now we want to particularly hone in on relations that do satisfy all of these, and how can we formally prove that? Okay, so let's take a look at this one over here. And it's going to be related to 3 below it. So we'll do 2 since that actually has a number there instead of a general integer n or natural number. So we're going to prove that the mod 7 relation is an equivalence relation. And just to be sure that we're clear about this, and there are different ways that we can think about this definition. So on the one hand, we could say, just trying to check the notation we've used in the past, that if I say that A is congruent to B mod 7, and just so you know, like in words, we would say that's how we would read that kind of expression mathematically. Then what this means is that A and B, they have the same remainder when we divide by 7. So this means, right, I can write B as 7 times something plus R, and I can write A as 7 times some other integer, and they have the same remainder basically when we divide it by 7 is one way to say this. It's probably not the definition that we're going to want to use in this proof, but I just want to be sure you're clear about that proof, or that way of stating it. So in other words, if I take, can put it like this, A minus B, then that tells me if I take the difference of A and B, right, those remainders would cancel each other out, those R's. So in other words, one way that is often useful for writing out what it means for 2 things to be congruent mod 7 would be to say that when we take their difference, either way, A minus B or B minus A, their difference is divisible by 7 because the remainders are going to cancel each other out. So some books might define congruence mod 7 in this way. If 7 is a divisor of the difference, then those 2 numbers are going to be congruent mod 7. So that's just some background about that. But any questions? Okay, so this is going to be a useful definition for us to keep in mind when we're going through this. So this can kind of be our definition for this congruence relation. basically we're saying that A is related to B if 7 divides their difference. That's the same exact thing as saying that. Okay, so I know that you're all probably not experts in modular congruence and things like this. So please let me know if you have any questions about this. These come up a lot when we're working with number theory, which is a lot where equivalence relations come up as well. So we're kind of operating in universe of mathematics called number theory here.
So if you were to have something like A is congruent to 3 mod 7, you would end up with 7 divisors A minus 3.
So if you had, say that again?
If you had something like A equals 3 mod 7, you would get 7 divides A minus 3.
Yep. Mm-hmm. Yeah, or it divides 3 minus A, either way. Yep. Okay. Yeah, so for example, we could have something like right, we think about 16 and 2. 16 is related to 2 by this relation, this mod 7 relation. Since 7 divides 16 minus 2, which is 14. Okay, or another way that you can think about that is I could write 16 as 2 times 7, and it has a remainder of 2. And I can write 2 as 0 times 7 with a remainder of 2. So these are just equivalent ways of thinking about this mod relationship. Okay. Any other questions?
Yeah, is mod kind of like our denominator, like what we're dividing it by? Is that like another way to think about it, or is that not accurate?
So what do you mean by dividing?
So like when you say like 7 and then the divides into A minus B, is it kind of like, can we think about the 7 as a denominator in out of a whole number, whether it's A or B?
It's more thinking like if you subtract A and B, then 7 is going to be a divisor of that result.
Okay.
Yeah, so I think that we want to stick with thinking with integers, so we don't necessarily want to divide things by 7 because that might take us out of the world of integers. But if we're safer saying that 7 is a divisor of that, yeah.
Okay, sounds good.
Okay, so any other questions about the mod relation? Okay, so let's try and check off these properties. So for the reflexive property, right here, what we're trying to show is for all A in the set A is related to A. You don't need to write this out. I'm just writing it up here for reference, just so we know what we are trying to do. So this is going to start with, well, we don't have any assumption or other than we're going to start with an integer, since that's our set here. And again, what we're hoping to show first is that A is related to itself. And so if we use this definition up here, then if I can show that 7 divides both of these two, the difference of those two things, then that should be enough to prove that they're congruent mod 7. Okay, 7 divides a minus a. Anything divides 0. So since 7 divides their difference, that is an equivalent definition to saying that they would be congruent mod 7. And thus, it's related to itself. Any questions? Okay, and for symmetric, this is saying that if A is related to B, that should imply that B is related to A. So I don't know, writing these out, I'm like a person that learns by writing things sometimes. So if I just write this out, sometimes that just beats it into my head what it is that I'm trying to do with these steps. It's a good way to kind of remember what these definitions are. And then that helps me kind of think about what is my initial assumption? What am I trying to get to? So that assumption is, okay, we've got two integers a and b that are related by this mod 7 relation. And again, we're hoping to show that when we flip that around, the order around, that we still have a relation. They're still related. So for this one, we've got A is related to B mod 7. So from this, we can use this definition for congruence mod 7 to say, okay, well, then it's going to follow that that's a 7 divides a minus b. So maybe here we've got a little bit more to say, since maybe it's not clear that if something divides a minus b, that it should divide also b minus a. That's what we need to kind of clear up here before I say that b is related to a. So we could say something like, thus, there exists some natural number so that a minus b is equal to 7 times that number. Yes, we don't need that to be a natural number. It could be an integer. So what do I need to kind of clear up before jumping down to that last sentence? Anybody have any thoughts about what remains? We haven't shown that B is related to A yet. We're really close. What kind of logical argument do we still need to make before getting down to that last sentence?
I kind of feel like multiplying both sides by -1 to flip the signs, but I don't know if that's quite going to work the way I want it to.
So you could multiply both sides by a -1. Sure, we've got an equation there. So this, and really what we're hoping to get here, right, is we just want to get some symmetry here. So I'd like to say that. Yeah, we've got that A and B are integers. We assume that that's our set up here. And by assuming that they're related, that means we're assuming 7 divides A minus B. So if 7 divides A minus B, that means A minus B can be written as 7 times some integer. And what I'd like to say is that when we flip these around, they're still related. So in other words, 7 should divide B minus A, and that's going to be enough to prove that therefore B is congruent to A mod 7. So there's a question about does 7 divide A and 7 divides B? No, we don't know that. What we know is that they have the same remainder when we divide them by 7. So 7 doesn't need to divide A or B, but what does need to be true is they have the same remainder, and that's why 7 divides their difference, because those remainders would cancel each other out. Yeah.
Are you saying A minus B over 7 equals N?
So we are trying to show that B is going to be related to A. So in other words, we would like to show that B is congruent to A mod 7, which means we would like to claim this. So kind of all three of these statements are saying the same thing. That relation is defined by saying if they're congruent mod 7, and then the definition of being congruent mod 7 is that 7 should therefore divide the difference. So all we're trying to do is work backwards from this. Let's prove this, which is going to imply that, which is going to imply that. And so I would like to show that 7 divides B minus A. We know that 7 divides A minus B. And the reason why that would be the case is these two things just differ by a negative sign, right? So that's not going to affect what integers are divisors of it. So that was a good idea as far as let's go ahead and multiply both sides of that equation by -1. Okay, or in other words, that would tell me that B minus A is equal to 7 minus N, since A minus B is 7N. So we can write B minus A as 7 times an integer. Let's see, there it is. So we could write that as 7 times the integer minus N. So this tells us if B minus A could be written as 7 times an integer, then 7 divides B minus A. Okay, just using that definition of equivalence mod 7 that we started the discussion with. So we're using that as our kind of definition of what the relation is. So basically, right, again, we just showed that if 7 divides A minus B, then it also divides B minus A. So that makes it this symmetric. Any questions about that piece of it? Okay, and then we've got the transitive part. And again, that's the implication that we want to prove. And this mod relation, again, we could just equivalently say A is related to B if and only if 7 divides their difference. Okay, so here, let's suppose we've got 3 elements, 3 integers, A, B, and C. And we're going to assume A is related to B and B is related to C. So A is related to B. So that means A minus B is divisible by 7, which means A minus B is 7 times some integer. And similarly, since B is related to C, let me not use N here, I'll use M. So let me just stop at that point. Any questions about why I started with this first assumption and then how I was able to go from that assumption to really claim that this and this are therefore have to be true? Okay, and again, just keep in mind what we're trying to prove. We're trying to prove that A is related to C. So just to kind of do some scratch work on the bottom, right, that means we would want to show that A is related to C mod 7, right, which means we would want to show that 7 is divides A minus C. So if I can show that A minus C is a multiple of 7, then we're good. So we're going to kind of go about it in this way, and we'll work our way up to that. So far, I know that A minus B is divisible by 7. B minus C is divisible by 7. So, and I would like to get something like this. Does anybody see what we might be able to do to try and get something, some equation that involves A minus C? There was a yes. Does that mean you want to share what's going on, Diane? Or
Combine the equations to get A minus B plus B minus C equals 7K plus 7M, and then combine terms factor out the 7.
yeah, so let's add those two relations together. We would get A minus B plus B minus C. Well, first of all, right, that equals A minus C. The B's would cancel out. And I know that that should equal 7K minus 7M. So maybe perhaps a better way of writing this out. It's going to change this order. Maybe that looks a little better. So we've got A minus C. I can write that as A minus B plus B minus C, and then use the fact that I know what A minus B and B minus C are to some extent. And since we got that 7 is now a divisor of that difference, then we know that they are related. There are congruent mod 7. Oh, can't fit it there. Okay. So that's our transitive proof there. And so if you're kind of getting the flow for these, yeah, like I think they kind of get increasingly difficult. So not that surprising that this took a little bit more work than the other ones. Okay, well, good suggestions. Thanks for getting those in the chat. I appreciate that. Any questions about this?
Wouldn't the K and M be addition?
You're right. Thank you. We did add them. Yes. Very good. Yes. So that would be a plus and a plus there. But otherwise, yes, I think we're still okay. Okay. So let me just say for 3 is asking you to do the same exact thing, except now instead of 7, we pick n. And here's how the proof of that is going to go. We can do exactly what we just did. Let me just kind of clear some of this stuff out. And there's nothing that we did in our proof that really mattered much about the number 7. So what I'm trying to do here in a slow way is go on to the next one. So here we're just going to generalize the 7 to any natural number n. And all I need to do here is take each of those 7s and replace it with an n, and nothing would really get affected. I think the only thing that I might want to change here, in addition, would be the fact that I did use an n in my previous proof. So I'm going to change that to a k. And then I'm going to change all of the 7s in this proof I changed my n's to k, first of all, that I had in my previous proof. And now I'm just going to change those highlighted 7s to n. And I don't think anything in my proof, for example, would be affected. So I'm just going to and that's fine, right? For example, the reflexive part is fine. If a is an integer, and if n divides a minus a, then a is congruent to a mod n. Great. And the same goes down here. So the point is, I could have just done that proof in general, but I feel like it's a little bit easier if we have a number there. So I did put a number in there, but that number was not the point. So this would have worked for any natural number. Now I need to remember where all of my 7s were. There was one here, here, here. And you could do the same for this one. So all I'm trying to say here is if you replace if I replace every 7 with an n in that proof, it's not going to affect anything. We had enough letters floating around without an additional n. So I think it does read nicer having a 7 there, but that's really just a placeholder for any natural number. All right, you guys doing all right? Okay, so just kind of keeping track here. Okay, so question number 4. Here we're talking about, we're no longer dealing with numbers in this case, but now our elements are lines in the Cartesian plane. So we've got Cartesian plane, that means R2. And our elements are lines in the plane. we're going to say that L1 is related, in this case, the relation here is P to L2 if those two lines are perpendicular to each other. So I didn't quite draw it right, but maybe those two lines are perpendicular to each other and therefore they would be related to each other. So far, we've had things that are in fact equivalence relations. The question here, the initial question is prove or disprove whether or not these are equivalence relations. So if we want to disprove it, we did a bunch of those last time, then we just need to provide a counter example. So what properties or property do you think this relation is not going to satisfy? I've got a quiz. I've got a poll for that. Let me open up that poll. So this relation, what do you guys think? My hint here is that this is not an equivalence relation. That doesn't mean all of them are wrong. I'm going to just say that at least one of them doesn't hold. I'm going to get a drink of coffee. I'll be right back. I'm going to miss my kitchen when I go back to teaching in a classroom. Remote learning, teaching, there are a lot of difficulties with it, but let's not look past some of the benefits. We have our pets, we have a kitchen, we have all sorts of things that are not going to be with us when we're back on campus.
Has there been any talk as to when that will be?
Yeah, it's going to be in the fall. So summer is going to be pretty similar schedule to what we have right now, a lot of remote classes. Fall is full bore as far as I know. That's right, you can do laundry, it's great. You can do laundry for other people too, maybe during class. Yeah, so we had a meeting with the, scheduling for rooms and all this stuff. And we said, are you gonna have like full capacity? Should we have half capacity classes? And they were like, nope, fill them up. So that's the plan. Like staff have started to get vaccinations and should be open for all of you pretty soon as well to start getting vaccinated if you haven't already been opened up. Okay, yeah, so let's see. So here we are with the poll. Thanks for the responses. Yeah, I can tell you that there's a wait list for faculty too. They had one faculty vaccination center now that we're kind of going off in this tangent. A couple of Fridays ago, it filled up in like 2 seconds. So I didn't get it, but there are other places around. So if you guys are, I spent the last couple of weeks trying to figure all that out. So if anyone is up and eligible for vaccinations and is trying to find a place to go, you don't have to go on campus. You can go anywhere. They're free. They had no idea who I was. They didn't even ask me for an ID, which is great. So it's really hassle free. I'll just say that. But if anyone's having some trouble with that, just let me know. But we're here to talk about math, so let's focus on that. That's what I'm specialized to help with. Okay, so yeah, here are the results that you guys had for that. So there was, at least going with the majority, we had a not reflexive, seems like it might be symmetric. transitive was on the fence here. So in order for this to be reflexive, right, we would need L1 would need to be related to itself. And a line, it's parallel. Any line is going to have the same exact slope as itself. So this is false. So since any line is not going to be perpendicular to itself, so here we kind of did proof by counterexample. And so if we want to show that it's not an equivalence relation, I just need to pick one of the relations that doesn't work, right? And the fact that the others may or may not work doesn't help or hurt this proof. And so the reflexive one is probably the easiest one to disprove. The other two properties, the symmetric property would work if A is symmetric to B, or excuse me, if A is perpendicular to B, or line 1 is perpendicular to line 2, then line 2 is perpendicular to line 1. And the transitive property, if we think about it, that one is not going to work, because if I have like L1 is perpendicular to L2, and L2 is perpendicular to L3, then L1 is actually going to be parallel to L3. So you can think about that. So the transitive property also doesn't hold, but the symmetric property does hold. Okay, any thoughts or questions? I want to give you guys a chance to practice this now before we go for today. Okay, so I'm gonna break this up. There are a couple of questions on the homework assignment that I might need to comment out. I think there are a couple of questions that ask sorry, I'm missing a whole bunch of good stuff in the chat here. Yeah, so sorry, did I catch up with what was going on, Diane? Sorry, I missed what you were saying.
No, you're good.
Okay.
I was asking, like, if instead of being perpendicular, L1 were like parallel. So in that case, the reflexive property will hold?
Yeah, so if that's a good point there. If instead of a perpendicular property, if we thought about the parallel property, that would be an equivalence relation. Yeah, good point. Since a line would be parallel to itself, if line 1 is parallel to line 2 is parallel to line 1, and the transitive property would work out in that case. Yep.
Okay, thank you.
Yep. Yeah, so I'm just kind of seeing here. Yeah, cool. So everyone is open for vaccines on Friday. That's awesome. I went through a drive-through place last week for my first shot. Super easy. Your arm will hurt for a couple days, but that's about as bad as it is. Okay, so just a couple of things as I was kind of saying, the we're not going to get to worksheet 19. I was kind of thinking about that. Let's just kind of hold off on that until after the exam. So there are just a couple of things on your homework assignment that might ask you to say, like, here's a relation, prove that this is an equivalence relation. That's what we're practicing now. Describe the equivalence classes. That part we haven't gotten to yet. So I'll just strike that out from the homework. I'll update that after class. So it's not going to mean that you have less questions, it means that maybe 1 or 2 questions, I'm just going to remove one part from that question. Okay, so I'd like you guys to, with groups, we can break up into 2 groups here. I'd like you guys to think about 5, try and prove this. So I'll just say this is an equivalence relation. So I'd like you to prove it, or just think about how you guys could prove that. I suspect that's going to take up all the time. If you happen to finish that up, feel free to think about 6, but I think that should take up most of the time left. So we've got about 10 minutes left. Maybe let's take about like 8 minutes or so talking in breakout rooms, and then we can spend the last couple of minutes just wrapping this up together. So let me open up these rooms. All right. Seems like we ran out of time. I don't know how the other room did. We finished everything. No, just kidding. We didn't get very far at all on our proof. So I think that we'll pick up with that proof next time, starting from there. Excuse me. So I just want to kind of clarify one change that I made is that I originally said exam 2 was going to be on worksheets up to and including 19. We'll stop the exam material with material on worksheet 18. So we'll deal with worksheet 19 after the exam. So on Monday, we'll review for the exam. We'll do some more examples. I think we should do some more work with equivalence relations, and then we can just talk about the exam in general. I will update your homework assignment to take out those parts that asked you about equivalence classes. So I will update that. But if you're working on your homework and you see that and you don't know what to do, just skip the stuff that asks about equivalence classes, but I will update that assignment. Okay, so sorry, we're out of time. We'll pick up with that example next time. And so have a nice weekend, everyone. If you do have some questions, I can stick around for a little bit. I've got a meeting at 12:30, but I can stick around for a few minutes after class. All right, well, thanks for a nice class, and I will see you guys on Monday.